Viewed as a system of information, the universe resembles a massive computer network. Galaxies, stars, and atoms function as nodes, constantly updating their states through interaction. Classical physics governs these interactions through local realism. This protocol dictates that a physical object is only subject to influences in its immediate surroundings. In this framework, if state A is to alter state B, a physical signal must traverse the empty space between them. This transit is governed by a fixed bandwidth limit, c, the speed of light. The limit applies to every known classical phenomenon, whether it's the transit of light, the radiation of heat, or the pull of gravity, all propagate at this finite velocity. Because this speed is not infinite, physical distance creates an unavoidable delay in how information moves through the system. At this scale, absolute synchronicity across a distance is impossible. One node must always wait for the signal of another to arrive. Local realism forces the universe to operate with a permanent latency, tying cause and effect to the constraints of space and time. 20th century physics solidified this latency into a rigid mathematical law. Albert Einstein's model of causality required that no information or influence could exceed this transmission speed. An instantaneous transfer of data would break the causal order of the universe, potentially allowing an effect to occur before its cause. Yet at the subatomic level, researchers have identified a native anomaly that operates outside this limit. This behavior isn't a faster signal. It represents a different method of state updating that doesn't rely on transmission at all. If a system can bypass physical latency, the model of a strictly local universe is an incomplete description of reality. To observe this anomaly, we have to generate it mechanically within a controlled environment. This hardware performs spontaneous parametric down-conversion, a process used to split individual high-energy photons. A laser fires a high-energy photon into a nonlinear crystal. As it passes through the lattice, that single photon occasionally divides into two lower-energy photons. These new photons do not behave as two independent discrete objects. They exist as a single mathematical entity, even when they are separated and moved to different locations. The creation event forces the universe to maintain two endpoints that share a single, indivisible codebase. This is quantum entanglement, a physical system defined by a shared variable. This is represented by quantum spin, the intrinsic angular momentum of these particles. Conservation laws demand that the total spin of the entangled pair must always equal zero. Consequently, the spins of the two particles must perfectly oppose one another at the moment of measurement. Before that measurement occurs, the system is probabilistic. Neither particle contains pre-programmed data or hidden variables that dictate a final spin direction. The exact orientation of the spin is undefined until the system is forced to resolve. Until then, the particles act as a single, uncompiled variable suspended across the intervening space. Measurement is the interaction that forces this unresolved state to lock into a single value. Consider these entangled photons separated by the width of the observable universe. When a detector intercepts the first photon to measure its spin, the system resolves, compiling into a specific state, like spin up. This resolution has a simultaneous effect on the second, distant photon. To maintain the zero spin requirement, it is forced to compile as spin down. No time elapses between these two resolutions. The measurement updated the shared variable directly, without traversing the space between the 2 points. This phenomenon is what Einstein described as spooky action at a distance. It challenged the core of his worldview because it functioned without any local contact. No signal, wave, or data packet moved across the void to deliver the state update. This result invalidates the classical assumption that the universe is purely local. The codebase of the universe updated a single variable in two locations simultaneously, without using the physical network of space. Entanglement demonstrates that the universe can execute operations across any distance in zero time. It is tempting to assume this zero latency update could be used to transmit data faster than light. However, the randomness of the initial measurement creates a hard technical barrier. A user cannot force the first photon to be spin up to represent a binary digit. You can only observe the random outcome the universe provides. You cannot modulate it for a receiver. Without control over the measurement, no coherent message can be written to the shared variable. The universe permits instantaneous internal updates, but it forbids the instantaneous transmission of usable human data. Even without data transmission, the fact of the instantaneous update remains. High-energy experiments, like those at the Atlas detector, confirm that this non-local behavior occurs even in massive particles, like top quarks. These results suggest that physical distance does not represent the underlying reality of the system. If two particles can update as a single unit without a signal crossing the gap, then at the level of the shared variable, that gap does not exist. The universe functions as a synchronized architecture, where the space we observe between objects acts as a feature of the rendering, rather than a barrier between the nodes. Fade to black. Stop speaking.